Okay, so you are basically comparing a manual calculation with the way R is doing it, right? So can you give an example of something that you calculated by hand and you did it in R and yeah, 3 divided by 2 into 3 to the power 3 minus 32. Okay, so what is the order of operations that you are following? Are you doing the exponentiation first, then the division multiplication, and then the subtraction? No, subtraction will come last, right? So I think the way R is doing this. Okay, I see. So R is basically what is the bracket order? So let me share my screen. Maybe we can walk through this together. You can see the R Studio window, right? R gets 8 points. Yeah. So it should be 3 by 2 times 27 minus 32, right? You do the exponentiation first. So yeah, so I think a rule of thumb that you can follow, I mean, if exponentiation is involved, is instead of bod mass, we call it uh, PEMDAS, PEMDAS. So basically, PEMDAS, yeah, PEMDAS, or you can call it PEMDAS. So P means anything involving parentheses. Okay, so parentheses means these brackets. So whatever is inside the brackets, you will evaluate first. And E means exponentiation. So basically taking powers like 3 to the power 2 or 3 to the power 6, something like this. And then multiplication, division have the same operator precedence. So if both are involved, you can do it in either order, and then addition and subtraction. Okay, so so welcome back everyone. So this is week 3 of the weekly live discussion sessions for the course Foundations of R Software. So again, we'll start by revising some of the concepts that were discussed during the week's lectures. And along the way, we can also clear some doubts or confusions if you have. So feel free to ask questions at any stage. So I'll go back to sharing my screen and the R Studio window. So again, please let me know if I am audible and if my screen is visible. So you can hear my voice, right? Hello. Okay, thank you. And you can see the screen also? Very well. So where we left off last time was looking at scalar calculations and scalar vector calculations. So we looked at something like, okay, what will you get if you have 2 plus 3, or if a variable a, which is 2, and a variable b, which is, let's say, 5, what do you get if you do a to the power b? So we looked at operations of this kind. And we also looked at, first of all, we looked at how to define a data vector. So let's say if I have a vector called VEC or VEC, and if I want to collect together, some numbers, then this is basically a vector. And now we can do vector scalar operations. So if we add the entire collection VEC with this variable A, what happens is an element-wise operation. So A gets added to A, which is a scalar, gets added to each element of the vector. So A is 2, so we get 1 plus 2, 3 plus 2, 4 plus 2, 0 plus 2, and 91 plus 2. And basically the same thing happens for other operations as well. You can do vec times A, or you can do vec divided by A, or even do an exponentiation here. And of course, subtraction and whatever. So now the next stage, so we'll actually come back to this vector scalar operation as a special case of what we are going to discuss next, which is the vector-vector calculations. So let me call this vec1, and let's define a vec2. So to start with, let's consider a case where vec1 and vec2 are of the same length. So they contain the same number of elements. So let's make this something 2, 8, 76, 12, minus 3. So let's see what happens if we do vec1 plus vec2. Now once again, as you can notice, what's happening is each element of vec1 is getting added to the corresponding element of vec2. So the first element gets added to the first element, second to the second, third to the third, and so on. And this will happen irrespective of the operation that we do. So same thing will happen for multiplication as well. So 1 times 2 is 2, 3 times 8 is 24, 76 times 4 is 304, 0 times 12 is 0, and 91 times minus 3 is minus 273. Now let's look at something different. Okay, let's have one more element here. So vec1 now contains 6 elements, and vec2, let's make it 3 elements. So now if I do vec1 minus vec2, I want you to notice very carefully what happens here. So vec1 and vec2 have an unequal number of elements. So element-wise operation will still occur. So the first one is 1 minus 2, then 3 minus 8, and 4 minus 76. But what happens to the rest of the entries? So what R does in this case is that it basically starts again for vec2. So vec2 has been exhausted. We have gone through all the elements, but vec1 is still not finished. There are 3 more elements. So what it will do is, this is 1 minus 1, 2 minus 2, 3 minus 3. This will become 4 minus 1, 5 minus 2, and 6 minus 3. So it will again repeat from the start. Now, here, one thing to note was that vec1 and vec2, even though they have unequal number of elements in vec1, which is 6, and number of elements in vec2, which is 3, 3 basically divides 6 completely. So you can partition vec1 in different sectors, and each of them will get operated by vec2. But what happens if we have, a number that is, so one of the vectors has elements which does not divide the number of elements in the other vector. So let's add one more element to vec2. So now if you do vec1 minus vec2, you get a warning from R that the longer object length is not a multiple of the shorter object length. But in spite of that, the operation is still conducted in the same manner. So again, we get 1 minus 2, 3 minus 8, 4 minus 76. Now what's next? Now this has 4 elements. This is not a divisor of the number of elements in vec 1, but we once again go back to the beginning. So this becomes 91 minus 2 and 2 minus 8, and we do not do a second operation with this 76. But this is something we need to be careful about. Now, usually when we'll do operations on vectors, we'll work with vectors having identical lengths, but one should not assume that, okay, the last three elements of my vector are 0, so I will not write those elements, and I'll assume that the operation will basically happen. The first three will get operated with the first three here, and the last three will get operated with 0. That will not happen. If you want the last three elements to be 0, you should explicitly write those elements as 0. So, say if we write this, and then if we do vec1 minus vec2, now things happen as they should. So 0 minus 0 is 0, 91 minus 0, 2 minus 0. So don't leave out the entries if you want them to be 0 or 1. So for subtraction or addition 0, or for multiplication division 1. Explicitly write out all the entries. And be careful about this length difference across different vectors. Now coming back to this, let's say vec2 is just a collection of a single number, which is equivalent to saying that vec2 is just 2. So now if you do vec1 to the power vec2, this is essentially we are coming back to a vector scalar operation. And as we had seen last week also, vector scalar operation happens element wise. So this is just a special case of the vector-vector operations. I hope that is clear. But if you still have some doubt regarding this vector-vector calculations, please feel free to ask. Yeah. Mm-hmm. The last one. Okay, I think I cleaned it up. But anyways, let's make this 2. Then what did we want? We want vec1 minus vec2. 1, 3, 4, 0, 91, or 9, 1 or 91. This is 91 or 9, comma 1? 91, okay. Vec2 equals 2, 8, 76, 12 and minus 3. Vec1 plus vec2. I'm not getting a warning message here. And please check, did you miss a comma somewhere, because of which it's treating 5-element object as a 4-element object? You can look at the right hand side also. Ah, 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 ah. That's why it's happening. Okay. Okay, so as far as the basic operations are concerned, we have already come across addition, division, subtraction, multiplication, exponentiation, and even the modulus operator. But there's one distinction, or actually a couple of distinctions, that we should be careful about what certain symbols mean. So as we have seen previously, if I do 1 divided by 2 in R gives me the fractional answer. Unlike a programming language like C, which will just throw away the fractional part unless you explicitly tell it that this has to be a fraction. So if you want to throw away the fractional part, then in this case you will do as dot integer. And then if you do 1 by 2, then only 0 is returned and 0.5 is thrown away. But as a default setting, R will give you the decimal answer. Now, what if I don't want the decimal answer? So division usually involves two results. There is a quotient and there is a remainder. So if you just want the quotient, so let's take a larger number, something like 53 divided by 22, something like this. So if I do the division like this, it will give me a decimal answer. But if I want to know what is the quotient and what is the remainder, we use a symbol like this. So note this one carefully. So this is still a slash, but sandwiched between two percentage signs. So now if you do this, you'll get 2, which is the quotient, as can also be seen from this here. So this is the integer part. And if you want the remainder, you'll use the double percentage sign without the slash in between. So this is right, because 22 times 2 is 44, 44 plus 9 is 53. And we have separated out the remainder and the quotient. You can basically divide, or you can store these results. So you can call it a variable. So 102, let's say percentage divided percentage, we'll do, let's say 12. So quotient is 8 and remainder is 102. So 12. Sorry, there should be an equal sign. And remainder is 6. So again, 8 times 12 is 96, plus 6 is 102. Okay. So I think, if I remember correctly, there was a question last week that how do we get R to do integer operations? I mean, because by default it is giving you the full decimal answer. So this is the way of doing this integer division and basically the modulo operation. Now, one good example of where this modulo operation is useful is, let's say, again, we have vec1, and what we want to know is how many even and which of the numbers in vec1 are even and which ones are odd. So basically, how do we define that? So the numbers that give a remainder of 0 when divided by 2 are even, and those that give a remainder of 1 are odd. So if I do this, so what is the remainder when the entire vec1 is divided by 2? You get 1, 1, 0, 0, 1. So let's compare it with vec1. The first entry was 1, which is an odd number, so the remainder should be 1. Second one is 3, again an odd number. 4 and 0 are even numbers, and 91 is again an odd number. So these small operations can have, larger applications. So for example, let's say you want to convert something into a binary, or so then division by 2 becomes important, taking the remainder becomes important. So that basically comes into the modular arithmetic field. But anyways, so these are simple operations that you can test and you can compare with handwritten calculations and see if R is performing the way it should. If it is not, then maybe we need to understand the syntax better. Maybe what we are trying to tell R, it's not understanding it correctly. So, and those are basically syntactical errors. So we need to be careful about that. But these three operations, so a backslash for the full division, double percentage for taking the remainder, and backslash sandwiched between the two percentages, giving basically the quotient of the division. So it's important to understand the differences between these. Okay, so is there any confusion regarding these operations? It is a quotient, yes. So again, if we go back to this vec1 modulo 2, that example, and if we put a slash in between, what it does is it's now giving you the quotient. So the first entry was 1. So 2 times 0 plus 1 is 1. So quotient is 0. For 3, the quotient is 1. For 4, it is 2. For 0, again 0. And for 91, it's 45. Okay, so if there are no more questions, then we can move ahead. One more important thing. This is something we've been coming across again and again, is the inbuilt functions in R. And a number of functions were discussed during this week's lecture. So, but what we need to keep in mind is how these functions act on scalar data versus vector data, or which of these functions expect you to give a collection of numbers, and which of them can work with just even one of them. So, let's say one of the functions we have encountered was as dot integer. So we saw if we give it some floating point number or some fractional number or some number which has a decimal part, it basically throws out that decimal part and gives you the integer part. Now, one distinction must be understood against what's our notion of approximating a number is, and what exactly picking out the integer part means. So let's say the decimal part is greater than 0.5. Now, when we are doing a naive estimation, the estimation is done in this way. So if it is 2.8, if it's less than, let's say, 2.5, we approximate it to 2. If it is 2.5 or above, we approximate it to 3. But the as.integer command does not do that. What it does is a simple task, throwing away the decimal part and just picking out the integer. So whether the decimal part is more than 0.5 or less than 0.5, it doesn't matter. As.integer will just pick out the integer part. So what function should we use to get the desired behavior or the behavior that we remember? So that function is round. So it does the rounding off to the nearest integer. So it's not the integer part of the number, it's the nearest integer. So the integer nearest to 2.76 is 3, not 2. And we can check because 2.76 minus 2 is 0.76, but 2.76, okay, let's do it the other way. 3 minus 2.0, 0.24. So 3 is the nearer of the 2. So that's what the output of the round function is. And again, the number that we are trying to round, if it contains a fractional part which is less than 0.5, it's rounded to the number, the integer which is less than this. So 1.234 is just 1. Now, there are other important functions, simple functions, but of great importance, such as, let's say, max. So what will max do? So if I give something here, okay, let's mix this up a bit. This is basically throwing out the maximum number of this collection. But mind you, we are giving multiple arguments here. We are not giving a collection of integers. A collection of integers would have looked something like this. Where we use this C function. But still it works in the normal way. So whether this is separate integers and you want to pick out the maximum of that, or whether it's a data vector and you want to pick out the maximum element, max will do that precisely. So let's use a older example. So vec2, if we write vec2 again just to see. So clearly we can see that for vec2 the maximum element is 76, and that's what max does. And same thing happens with min. So minus 3 is the minimum. Now whether you apply min on a vector like this, or if you apply it on just a random sequence of comma separated numbers. So it works in the desired manner. But there are some functions which do not follow this behavior. One example is, let's say if I want to take the mean of 2 and 3. Now we know mean of 2 and 3 is what? 2 plus 3 by 2, it's 2.5. But you get 2 here. And let's compare it with the same action on a vector. So let's write out vec2 once again. So what do we expect the mean to be for vec2? If we do the computation by hand, then 2 plus 8 is 10, 10 plus 76, 86, 86 and 12 is 98, minus 3 is 95, and we divide by 5, we get 19. So we see that in one case, the mean function is giving exactly what we expect it to, but in the other case it is not. So can you guess what is happening here? Yeah, it is taking only the first argument. So let's study this command. Let's now, if we come back to mean, you see, it only takes a single argument. There are other options, trim equals 0, and so we are not concerned with that, but it takes a single argument. So that's why it is taking 2 and ignoring 3, and it's giving me a mean of 2. So it is only considering one number, which is 2, and the mean of one number is that number itself. But if that single argument is a vector, then it does the operation on the entire vector. So this is basically equivalent to. So if you want the desired behavior, it's best if we define this collection as a vector. Now it's giving 2.5, which is what it should. Now, one could have been misled by looking at these two examples, and that would have been a wrong impression, was that, okay, 2 plus 3, 5 by 2 is 2.5, so maybe mean is throwing away the fractional part. But for vec2, this came out to be 95 by 5, which is 19. So for integer values, it is giving the integer itself. But for fractional values, it is throwing away the decimal. But that would have been wrong. That is not what is happening, as we have seen here. If we define 2 and 3 as a collection, we get 2.5. So mean is not throwing away any fractional parts. Now, other than this, okay, there is some other popular or useful, functions that have been discussed in the lecture. So let's briefly touch upon them. So ABS, as the name suggests, is for calculating the absolute value. So if you put minus 200, you get 200. If you put vec2, you'll get a vector with the absolute value of each of the entries of vec2. So the first 4 entries were positive anyways, so they are positive now. They're still positive. The last entry was negative, so that becomes yes. Even if I do minus of vec2, it will still give you the same thing, because minus of vec2 has the first 4 entries as negative, last entry as positive, but does it matter? So absolute value will make everything positive. We've already seen round. Another useful function is the square root function. So if we do this on vec2, now you see what has happened. So for the positive entries, the square root is defined, and this becomes the square root of 2, the square root of 8, square root of 76, square root of 12, and these are all approximate because none of the elements of vec2 is a perfect square. But for the last quantity, it returns a nan, not a number, because the square root of a negative number is not defined. So how do we remedy this? So one way is you convert vec2 to a complex number. Now, as you can see, the output is also made up of complex numbers. So the first 4 entries, which were greater than 0, their square root only has a real part. The imaginary parts are 0. The last entry, which was a negative number, for that the real part is 0, but the imaginary part is a number, non-zero basically. So this is also something we have to be careful about when we write larger programs, that what can be some sources of nans in our code. And based on that, we have to do suitable modifications. Now, as we've seen, the round function basically does a rounding of sorts, so to the nearest integer. But the round is giving you the nearest integer, but let's say you want specifically the closest integer which is smaller than the number, or the closest integer which is larger than that number. So that is where the functions called ceiling and floor come into the picture. So what ceiling does, it takes you to the smallest integer, which is just larger than the number you are concerned with. So if you do 31.2, then the smallest integer, which is just larger than 31, is 32. That's what ceiling will do. And if you do floor on the same function, it will give you the largest integer, which is just smaller than this number. And that largest integer is 31. So we are not doing a rounding off here, because 31.2, if we had rounded off, it would have always been 31. Getting 32 from this, that means we are invoking this ceiling function. So again, this is important to know the difference between these four functions. So what it means to take the ceiling, what it means to take the floor, what it means to just take the integer part, and what it means to round off a number. As you can see, 4 out of 3 of these functions are giving the same output. But it's important to understand the differences, because depending on the context, one or the other may be useful, the other may give the wrong answer. Yeah, so they're giving the same output for 31.2. But if I use a different number, let's say we make it 31.72, then round will make it 32, the closest integer. But if you do floor on 31.72, it will still give me 31, because 31 is the largest integer, which is just smaller than 31.72. Round and ceiling will give the same function. Yeah, round and ceiling are doing the same job now. They'll give the same output. In this case, they'll give the same output. So what we need to understand is, for these four functions, the outputs can be same or different depending on the number we are operating the function on. So that's where we need to be careful, that from one example we can't, understand that, okay, for all the numbers, these three will give the same output. That's not true. Or we say that for all the numbers, round and ceiling will give the same output. That's also not true. So they may or may not give the same output depending on what number you are working with. So that's why it's important to understand differences, that you should know clearly what do you want as an answer. If you want just the integral part and you're not doing any estimation, you just want to throw away the decimal part, use as dot integer. If you want to round it to the closest integer, use round. But if you want the integer just above or the integer just below, use ceiling and floor. Oh. Now, of course, again, there are some functions that can take multiple arguments and give you different outputs. So if you do sum on 1, 4, 2, it just adds 1 plus 4 plus 2. And if you do the same thing on, let's say, a collection, which is 1, 4, 2, or a data vector, it again does the same thing. So yeah, the ceiling of an integer. Let's see. What do you think? So by definition, ceiling is the integer which is just larger than it, right? So if it's larger than or equal to, it's larger than or equal to. So the ceiling of an integer is the integer itself. And similarly for floor, it's again the same integer. Okay, so just like sum, we can also do product. And this is similar to doing 1 times 4 times 5. Now, just as we can have, a long line of operations, so we add two numbers, we divide them by something else, and we multiply it with something else. Similarly, we can do a nesting of these operations. So let's say we take the sum of 23 and 41. And with that sum, we want to do a multiplication. So we do this output and we multiply it with, say, 2 times 2. Sorry, 2 to the power 2. And then we can maybe subtract 12 from this, right? And ultimately, I want the answer to appear as just the integer. Now, let's unpeel this layer by layer and see what would have happened if the functions are removed also. So if we had not taken the integer value, oh, this was still an integer. Anyways, so it's 12, then 12 more is added. If we don't take the product, it basically gets divided by 4 because 2 to the power 2 was 4. And ultimately, this is just 23 plus 41, which is 64. The point I'm trying to emphasize is that just like you can write these long expressions with multiple operations, with the familiar addition, subtraction, division, exponentiation, you can do the same thing for different functions. Okay. Now, one more common function is the logarithmic function. Yeah. Which one? Yeah. So if you just do prod of sum, then you're not giving a second argument, right? Did you close the bracket? Okay, I'll type it and tell me if this is exactly what you have typed. What else? Hmm, hmm, yeah, and yeah. Hmm. You have one extra bracket. This bracket is extra, so that's why you are getting an error. Remove the bracket after 12, because see, for sum the bracket is closed. You have given two arguments and the bracket closes. For product also you have given two arguments and the bracket is closed. So the last bracket is extra. Yeah, sure. The next family of operations is just like we had done this 2 to the power 8. There's a special function called exp. If I do exp of 2, it's basically there is some number that is getting squared. So what number is that? That can be checked by doing exp to the power 1. So this number 2.718282. So this has been terminated up to this point, but it has a longer representation. So we just denote it by e, special symbol. And this is the value of e. And when you take powers of e, you just use this function exp. So you don't have to explicitly do this 2.178.282 to the power 9 or whatever you're working with. So you can just do exp 9. And this exponential e, it appears in a number of places in scientific calculations. So that's why it's important. But just like pi, which we normally approximate as 3.14 or 3.1415 something, e is also a non-recurring real number. So the decimal part just keeps on going, non-recurring, non-terminating. So that's why we have this built-in exp function. So you don't have to remember the value of e to arbitrary number of decimal places. You can just invoke exp to the power, exp and then the argument. Now again, what happens if I give two arguments? You see, exp only requires one argument, but what happens if I give a vector? Then this works. Now, there's another thing that should be kept in mind. This notation, the way this has been written, 7.389056e plus 00, or 2.980958e plus 03, and so on. So what does this part mean? E plus 00 or E plus 03. Now this is very important, so please listen carefully. This, what to the power 3? 10 to the power 3, yeah, correct. So this is scientific notation, and it just means that, so if you look at this one, and let's copy this and try to convert it to integer. Now, by just looking at this part, one may have guessed that, okay, the integer would just be 2. But that's where this E plus 03 comes into the picture. So what this means is that this number is actually 2.980958 times 10 to the power 3, or in other words, 1000. And if you multiply it by 1000, it becomes 2980. That's why when you do as.integer on this, it gives 2980, not 2. So it should be clear what does this notation means. So this E does not refer to this E. Okay. And when there is a negative number, that just means it's divided by 10 to the power that, or 10 to the power minus of that. So if I do E minus 02, okay, 12E minus 02. So it's 0.12. So this is 12 times 10 to the power minus 2, or 12 times, or 12 divided by 10 to the power 2. Is the same. Yeah, yeah. It should give the same result. No, I just wanted to show, I mean, what this actually means. I wanted to show that this is not just this number. So this is actually multiplied by 1000. So we are not doing this. This was just a way for me to show the difference between just this number and this number with an E plus 03 attached to it. So I just wanted to emphasize that this is not 2 point something. This is actually 1000 multiplied by this whole thing. But if you're asking why we use this notation at all, then that is just for, this is small. This is just 3. So you can multiply by 1000. But look at this one. This is, if you want to write this number, it says 10 to the power 33 is there. So R will not print out the whole thing. So let's try what this gives with as integer. See, so this crosses the limit for the integer storage. So, but you still want to report such value. You don't want to say this is infinity because it's too large. So the best way to do that is just separate out the power of 10 and separate out the, with one leading place here and then some decimals. This is just a convenient way to express big numbers. Yeah. Now the opposite of exponentiation is logarithm. So by default, if you do logarithm of any number, this is calculated with respect to the base being e. What does that mean? What this means, if I do exp 1, which is just e to the power 1, the logarithm will be 1. So this is what the log is returning, that exp to the power what is that number. So the meaning of this 0.6931472 when we did log of 2 is that 2 is actually equal to, or let's say exp of this number is actually 2. That's what it means. But sometimes, yeah, I think the inbuilt functions that R provides has log of 2, log base 2 and log base 10, so that with the desired behavior. So let's see if we have other variants or not, or maybe a variant of log where we can, yeah, yeah, yeah. So log B, I think you can modify the normal log function also. So it takes 2 arguments, and by default, the base is set to E, but if we do base equals 5, yeah, 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 because, yeah, because E itself is a positive number, and no power of a positive number can be a negative number, right? But let's say we do the log of, let's do the log of a number, negative number explicitly, and we can show where this will work. So let's say log of minus 125, and we set the base equals minus 5. Okay. So I think internally what is happening is it's taking a log of this with respect to E first, then dividing with the log of minus 5 with respect to E first. That's why this is not working. Yeah, but just taking the default log of a negative number will give you an N. So I thought that maybe you can modify the base, but even if you modify the base, this is not working. What about log B? Still doesn't work. Okay, so the lesson is log of negative numbers are not defined anyways. But since we know minus 5 to the power 3 is minus 125, we still can't do the inverse operation here. So the reason of this is that usually we want to deal with smooth functions. Now, log of very small positive numbers is still defined, let's say, but you see, you start seeing errors now. Okay, so no, this one is right. But the moment we do log of 0, we get minus infinity. So if we try to plot a graph for log, there is a discontinuity at 0. So because of that, this is completely rejecting the negative numbers, even if we define the base to be a negative number. Because by common sense, one would have expected it. Yeah. Yeah. So the thing is, that is more like saying exp of minus infinity is 0. So what does that mean? That is just 1 by exp of infinity, right? Now exp of infinity is a very large number. So if we take the inverse of that or divide it from 1, you'll get 0. That's what it's trying to say. That 1 by infinity is 0. So that's why the log of 0 is minus infinity, or log of minus 0 is also minus infinity, because 0 and minus 0 are the same number. But you can't say the same about any other number. 0 is the only number where you can say x equals minus x, right? Okay, so let's move ahead. The final topic that was discussed in this week's lectures, and that was how to define a matrix. So matrix is the simplest tabular structure, which is one level above the vector. So if you look at a vector, what is this? The way these numbers are arranged, you can either think of it as, okay, there is just a row where we have these 5 entries. But we can go a level above. And to do that, we define a matrix. And the definition is, first you define the number of rows. Let's say we want 2 rows and we want 5 columns. So the first argument gives the number of rows, second argument gives the number of columns. And then you want to fill in some data. So you know 2 times 5 is 10. So your data should be such There are some 5. There are 10 elements there. 1, 2, 34, 50. There's 5. So how much is it? 3, 3, one more. What happened? What did I miss? So I should say data equals. Yeah, now it's working. Okay. So now it's important to see how these numbers are getting arranged in this table. So see 1, 2, 34, 5. So this goes 1, 2, 34, 5, then 21, 76, 1, 3, 45, 12. So this is filling it column wise. So you fill the first column, then you fill the second column, then the third column, and so on. What if we have less number of entries in my data vector than I want to fill? Now, basically it is circling back, I think. It's starting from 1 again. So let's decrease a few more numbers. So now we have chosen only 6, but we want to fill in 10 entries with just 6 numbers. So again, it goes 1, 2, 34, 5, 21, 76. So that's where you exhaust the data. So, but the matrix still has some more entries. So what R is doing, it's again starting at the beginning. So it again goes from 1 to 34 and 5. But again, this is something we must be careful about. If we want to fill in zeros and we don't want the entries to be repeated, we should explicitly say that we want the last 4 entries to be 0. If we don't do that, or let's say some other number, we want the last few entries to be 1, all of them we want them to be same, then we should explicitly mention that. If we miss these entries, R will automatically just restart the filling in process and start from the beginning again. And maybe that is not what we wanted to happen. Now, let's say instead of filling the numbers column wise, we wanted them to be filled row wise. Now, why that may be important? Now that will come into the picture once we start defining what these rows and columns mean. So maybe what the rows define is the name of a student, and what the columns define are the marks obtained by that student in different subjects. So student 1, these 5, okay, these values are not representative of any realistic marks, but just bear with me. So then the way we are entering the data becomes important. So if the order in which we are entering is that, let's say for the first subject, I enter the first student's marks, the second student's marks, then for the second subject, I enter the first student's marks, then the second student's marks, and so on, then this is fine. But if instead, the way I'm entering marks is that for all 5 subjects, I enter the marks of the first students, then for all 5 subjects, I enter the marks of the second students, then this output is not what I want. And how do I get the desired output? Is by using this argument by row, and we set it to true. So by default, by row is set to false. If we set it to true, now things fill row wise. So I get 1, 2, 34, 5, 21, which is the first 5 entries, and then 76, 1, 1, 1, 1, 1, the last 5 entries. Now, let's say we store, okay, let's change a few of them. Let's say we store this matrix in some variable. Let's call it M. You see, it's stored in the category of data, and we can do some operations on M. First of all, if we want to access the elements of M, let's say I want to know how much marks did the second student get in the third subject. So then we'll do what is called subscripting, where we mention the row number first, and then we mention the column number. So M2, 3 means we look at the second row and we go to the third element. And this returns 10. Okay, don't look at this one. We should Right, M again. So this is 2 comma 3 is 10. And this is not the same as 3 comma 2. Now, can someone tell me what does this mean? Subscript out of bounds, and why an error is being thrown here? Anybody? I mean, just remember the first entry means the row, the second one means the column. So, can you see what is the error here? Hello? Okay, so what's happening is we are calling for a row which does not exist. There is no third row here. So we are asking for a data stored in the third row, but the third row does not exist. That's why there is an error. Now you can do other things with a matrix. So you can ask what is the dimension of that matrix, and the values that you get, dim 2, 5. So dim of m is 2 and 5. What this means is that there are 2 rows and 5 columns. Let's see if this output is. So now if you want to see the number of elements inside the matrix, you just multiply the number of rows and the number of columns. So you can just do this product operation on the output of DIM. But you can, pick out the specific information as you please. So n row for m is 2, and sorry, and call for m is 5. Okay. So are there any doubts or issues you're facing with this? And please feel free to ask. Okay. So m2 comma 3, whenever I do something like this is called subscripting. So m is a matrix and I'm subscripting it in this manner. So I'm basically asking the question, what value? So m is storing several values at different locations. So this is one location, the second location, and so on. So m2 comma 3 means that what is stored in the second row. So you start 1, 2. So this is the second row and the third column. So stay within the second row. This is the first column, second column, third column, and that value is 10. So that is what is being returned. But if you do something like m3 comma 2, and there is no third row here. That's why it's saying the subscript is out of bounds. So the bounds for row is 2, for column it is 5. So if you ask for, so I guess if we do something like m2 comma 7, it should give us an error because there is no seventh column. We only go as far as the fifth column. Okay. So if there are no more questions, then we can end the discussion here.